So now we're going to move on to exponential equations. One of the properties that's really good to know, we call it the one-to-one property. Right here, the one-to-one property. It means that if you have a to some, okay, let's start over. If you have a to something equals a to something, see how the bases are the same? That means the exponents must also be equal. Okay, so this is how that works. If you're looking at this equation, you try to ask yourself, so can we make the bases on both sides the same? So 4 to the x equals 4 to the something. Well, 1/4 is 4 to the -1, right? Since these bases are the same, that means the exponents are also the same. So x must be equal to -1. So how about this one? Can we make these bases the same? Well, 1/10 is the same as 10 to the -1, right? But since it's raised to an x, I think we can say it's 10 to the -x. Isn't that what 1/10 to the x means? 10 to the -x? Alright, so then we have 100. Well, 100 is 10 squared, right? These bases are the same, which means the exponents are the same. -x equals 2, which means x equals -2. Let's solve a few more using the one-to-one property. We have 2 to the -x equals 1/8. Well, 2 to the -x, 1/8 is the same thing as 8 to the -1, right? Can I rewrite this 8 so that it's a 2? 8 is the same as 2 cubed, right? Well, what do you do with a power to a power? Don't you multiply the powers? So 3 times -1 would be -3. These bases are now the same, which means the exponents are the same. So -x equals -3, which means x equals 3. Let's try number 4. Let f of x equals 3 to the 4 minus x and find x such that f of x equals 1/9. So they're telling us that instead of f of x, we want to put in a 1/9. So a 1/9 goes right there. 1/9 equals 3 to the 4 minus x. Well, 1/9 is the same thing as 9 to the -1. But 9 is the same thing as 3 squared. Power to a power, you multiply the powers. Now the bases are the same, so are the exponents. So -2 equals 4 minus x. So we need to subtract 4, and we get -6 equals -x. Divide both sides by -1, so x is equal to 6. Okay, compound interest. If a principal P is invested for T years at an annual rate R, compounded n times per year, then the amount A, or the ending balance, is given by this formula. So this is what that means. A is the final amount, or the ending balance. P is the principal. R is the interest rate. N is how many times per year interest is compounded. And T is the number of years. It's very important that you know T is in years. Find the amount or future value, that would be A. So we're looking for A. When a principal of 20,000 is invested at 6%, compounded daily, this is your N, for 3 years. Okay, so we have A equals your principal, which is 20,000, times 1 plus your rate, which is 0.06, divided by n. It's compounded daily. Daily would be 365 times a year. So 365 all to the 365 times t. T is 3 years. So now all you have to do is put all that in your calculator. The key to this is make sure you do not round anything until the very, very end. So this is what it looks like when I put it in my calculator. 20,000 times 1 plus 0.06 divided by 365, all to the 365 times 3. When I calculate that, it gives me the final amount of $23,943.99. That means that you actually earned $3,943.99 in interest. So what about continuously compounding interest? If a principal P is invested for T years at an annual rate R compounded continuously, this is your key word here. On the previous page it says it's compounded daily. It'll give you a time amount that it's compounded, like daily, monthly, yearly, quarterly, something like that. On this problem, it says it's compounded continuously. That's how you know to use this formula. Then the amount A, or ending balance, is given by this formula. A, final amount, equals P, that's your principal. E is a number in your calculator, and if you have the TI 84 plus, E is actually the division button, or you can use your LN button. Either of those will work. R is your interest rate, T is your time. And time again is in years. Find the amount when a principal of $5,600 is invested at 6.25% annual rate, compounded continuously for 5 years and 9 months. Okay, so we're looking for A again. P is going to be $5,600. R is 6.25%. That's 6.25%, or 0.0625. Compounded continuously, so we know we use this formula, for 5 years and 9 months. So T is 5 years, 9 months. That's 5 years and 9 out of 12 years, right? 9/12 of a year. Well, 9/12 is what? 3/4. So you can use a fraction. In this problem, it's a nice decimal, so you could actually use 5.75 years. If it's not a nice decimal, like if it repeats like 0.33333, you want to use a fraction, because you never ever want to round any of these numbers until the very end of the problem. So A is equal to 5,600 times e to the r 0.0625 times t, which is 5.75. So when I put this in my calculator, it's going to look like this. 5,600 e to the 0.0625 times 5.75. It should look something like that. And I get $8,021.74. $0.63. The radioactive decay model. The mathematical model of radioactive decay is based on the formula A equals A sub 0 e to the RT. Doesn't that look a whole lot like A equals PE to the RT? That's because they're extremely similar, which gives the amount A of radioactive substance remaining after T years, where A sub 0 is the initial amount present and R is the annual rate of decay. So, you can use this formula as a decay or a growth formula. The difference is right here. If it is a growth problem, then R is positive. If it is a decay problem, it's decreasing, right? So the rate will be negative. So that's the difference. A is the final amount, just like this A was the final amount. A sub 0 is the original amount, just like P is the original amount. This particular time doesn't actually have to be in years. In these type problems, you just use the time that they give you in the problem. So let's have a look at one. Finely chipped spear points shaped by nomadic hunters in the Ice Age were found at the scene of a large kill in Lubbock, Texas. From the amount of decay of carbon-14 in the bone fragments of the giant bison, scientists determined that the kill took place about 9,833 years ago. Carbon-14 is a radioactive substance that is absorbed by an organism while it is alive, but begins to decay upon the death of the organism. The number of grams of carbon-14 remaining in a fragment of charred bone from the giant bison after T years is given by this formula. So they gave us a formula here, where R is this number. Find the amount present initially and after 9,833 years. I want you to recall the formula on the previous page. A equals A sub 0 e to the RT. Compare this to the one they just gave us. And then look at the question. Find the amount present initially and after this much time. So we're looking for two different amounts. The initial amount is whatever that number is. So the initial amount will be right there, 3.6 grams. They actually gave that one to us, right? And then after 9,833 years, that's your time. That just goes here for time. So A is equal to 3.6 e to the rate, which is negative 1.21 times 10 to the negative 4th times time, which is 9,833 years. So what would this look like in my calculator? 3.6 e to the parenthesis. If you want, you can put another parenthesis there. Negative 1.21 times 10 caret negative 4. So that's the first one. Times 9,833, and then close that one. It should look something like that. So the amount present after all that time has passed is going to be approximately 1.1 grams. So does it make sense that there's less there after almost 10,000 years than there was at the beginning? It does make sense because this substance is decaying, so it's decreasing.